part about what we're doing now is to not get it confused with the angles. It's totally different thing now. So normally, like up till right now, we'd look at that and say, oh, that's an inside angle. It's 1/2 big arc plus small arc, right? Well, now we're not looking at the angles. We're looking at the chords that make them, okay? Because those have relationships too. So the chord product theorem, and I wouldn't worry. I think a little bit of our problem with some people is you're so busy writing all this stuff that you lose what we're saying. So listen and just do a quick paraphrase. Just write 1 or 2 words that explain to you how to do it, or a picture. Okay? So in the chord product theorem, the chord product theorem says that if you take the 2 pieces, see how the chords intersect each other? If you take the 2 pieces that are made from the intersection, the product of these 2 equal the product of those 2. Okay? So in letters, it's AB times BD equals CB times BE. Just anywhere, just in it anywhere. Okay, so I always think it's easier if you have numbers. So like if this is 6 and 6 and 9 and 4, say that. Then what we're saying is AB, which is 6, times BD, which is also 6, should equal CB, that's a 4, times BE. So 6 times 6, 36, 9 times 4, 36. So it's saying the product of these 2 equals the product of those 2. And so can you kind of see how we'd use that to solve for missing pieces? Like if I had 2 chords like that, and I had a 10 and a 2 and a 4 and an X, then we could find that missing piece by doing 4 times X is equal to 10 times 2, right? So 4x equals 20, x equals 5. Does that make sense? It's very basic. Like I said, it seems like the hardest thing is remembering we're not dealing with angles. We're doing segments now. All right, so, and a good example of this, in archaeology, they actually use this. Like somebody dug this little piece of a shield up. They dug it up, and they want to know how big was it when it was new, before it got all destroyed. So what they did was they drew a chord through the edges, right? And then they drew another chord that was a perpendicular bisector, okay, that started there, but they didn't know where it ended. They don't know. And they said, okay, if this is a perpendicular bisector, we know how wide that is. That's, let's say it's something smaller. Let's say it's 5 feet, 4 feet. Okay? So we know that this side is 4 feet, and since it's a perpendicular bisector, this side is also 4 feet. They measured it, right? And they know the distance from here to here is 2 feet. And so they want to know how long the whole shield was. So they call that x. So how would I find that out? Right, 4 times 4 equals 2 times x. 4 times 4 is 16, and x is 8. Okay? No, actually, it ends up being an oval because this is 8 across, but then this is 10 this way. Yeah, yeah, yeah. Good question. Yeah. Oh, I thought you. Okay. All right. And they can use that like, you know, they can tell by the how big the sword is, how big the people are. You know, like they're not going to have a teeny tiny shield if the person's really big. And conversely, if the person's really small, they can't be carrying a giant shield. So they help that also to kind of see, make some assumptions about the people that are carrying them too. All right, so that's chord. Then we have secant. Okay, now secant it stops at the circle. It doesn't really go past it because it's a line. So if it's a line, we could never measure it. So it wouldn't have any relationships. So we stop at the edge of the circle. Okay? And the secant theorem says that these two lengths are related because if you take the external part, so EB, times the whole secant, EA, it's going to be equal to the external part of this one times the whole thing. So let's say we made this is 5, and this is x, and this is 6 and 4. Then what we would, the secant theorem says that the external part, 5, times the whole secant, which is 5 plus x, right? Wouldn't the whole thing be 5 plus x? Is equal to the outside of this one times the whole secant, which is 4 plus 6. All right, so to solve it, I would distribute. I get 25 plus 5x equals 6 times 10 is 60. Subtract 25, and that'd give me 5x equals 25, 40, 35. So x is 7. So we can find the length of AB by solving for x. So the secant theorem says external times whole equals external times whole. Okay? And a couple things people do that you should avoid. One is it's not internal times external. It doesn't work like that. It's external times the whole thing. And when you're finding the whole thing, do we multiply those two? No, we add them. For some reason, people like just to do this times this or this times this times this. Like they like to multiply way more than we should. Does that make sense? Okay. The last theorem is the secant tangent theorem. The nice thing is you treat secants the same. So it's still the outside times the whole thing for the secant half, but the tangent half doesn't have an inside part, right? It can't be outside times the whole thing because the outside is the whole thing. So instead, we just take that part and square it. We just multiply it by itself. So we basically just use that part twice since we don't have another part. So in letters, CB times CA equals CD squared. So if I put numbers on there, it would be like 4, 5, and 6. It would be 4 times 4 plus 5 equals 6 squared. Okay, 4 times 9 is 40. It's 36, and 6 squared is 36. So that works. Okay? Yes? No? All right, let's put it to the test. All right, which theorem are we going to use for that one? Secant, secant. Good. Somebody give me, CJ, give me the formula you would use. Well, that's a start, right? That's part of it. So 5 plus x and 6 plus 6. Well, what do you multiply those by? Because 5 plus x will be the whole thing. So we multiply that by the outside. So it's going to be 5 times 5 plus x. And on this side, it would be 6 times 6 plus 6. Again, distribute, and that gives me 25 plus 5x equals 6 times 12, which is 72. Subtract 25, and that gives me 5x equals 47. And then just divide by 5, and that gives me x equals 9 2/5. Decimals are just so little used once we get past geometry. Right, right. Get in the habit of writing as fractions. Okay? Then what theorem is this one going to use? Chord, chord. So what would that one be? Laura? Okay. Do you have chord, chord? Which one is chord, chord? Right. Good. So we get 4x equals 27. Divide by 4, and I get x is 6 3/4. And last but not least, this one is secant tangent. Joyce, what would the formula be for that one? 4 times the whole thing. Good. Good. So 4 times 4 is 16. 4 times x is 4x equals 36. Subtract 16, you get 20. 4x equals 20, so x equals 5. All right? We're not going to do like fancy word problems. Let me just quickly add that. So if it doesn't go all the way through, it's not a secant, so you just use Pythagorean theorem.